Hello everyone, my name is Raghu Prabhudeva. I'll be presenting a brief overview on FIRE today as part of the CS6440 course curriculum. So as part of this FIRE presentations, we'll primarily talk about what FIRE is, what were the background or the reasoning for FIRE standard to evolve, what are the typical capabilities that FIRE provides, what are the typical use cases that we see FIRE as being one of the driving factors, and then we'll talk about what are the current positives that we see about FIRE as a standard, and what do you think that there are potential hindrances or difficulties or challenges that we see with FIRE as a standard. Then we'll probably go ahead and do a small implementation of the FIRE server. How do we deploy our own FIRE servers? Then we create a sample FIRE client and do some kind of basic operations on some of the resources, and we'll see the usage of APIs, basically CRUD APIs, to operate on the FIRE resources. So that would be the flow of today's presentation. So before getting into much more details, let's understand what FIRE stands for. FIRE is basically an interoperability standard for healthcare that was created in order to exchange information electronically or digitally. So the acronym for FIRE is basically F stands for fast. This gives us that means that the thought process was that we should be able to evolve and integrate, design and implement systems very quickly, and the use cases very quick and fast, primarily concentrating in the healthcare sector. Interoperable basically enables different healthcare systems to integrate and work, being vendor neutral. That means that you are no longer tied to a specific vendor implementation, so that you have choice or options to kind of switch vendors. Then our resources are the basic building blocks on which the FIRE protocol operates, or the basic building block of exchange of information is a resource in the case of FIRE. So let's talk about a brief origins of how did FIRE arrive at this stage. The primary thought process behind the FIRE as an evolution of FIRE standard has been that there was an increased need for healthcare information electronically. If you look at a simple example of how patients move around the healthcare ecosystem, people move from places to places and trying to switch practices and things like that. They would like to carry their health information and accessible to different healthcare provider and switch practices. And today, or in the previous scenario prior to FIRE, these systems on which these practices were tied to were pretty much tied to a specific vendor. They were not interoperable, so you could it was very difficult for anybody to carry their health history and information or exchange that with the new practitioner. That was one of the biggest bottlenecks. Then the other big thing is that with the penetration of IoT or mobile devices and cloud-based application, it is becoming increasingly more important that the accessibility of the healthcare data on different platforms is very much necessary, coupled with the ability that we would like to do any kind of real-time clinical decision support or do any kind of research on data. Standardization and accessibility of that is primary importance if you want to do any kind of machine learning around the healthcare data to kind of predict any kind of diseases or doing any kind of population health capabilities. Then, of course, that we would like to use technologies which enable systems to integrate faster, people to build new applications, and open to the app developers, so that there is innovation in that space. So that was primarily some of the reasons I would say that that's how felt there was a need for FIRE as a standard. So as I discussed about a few use cases that we generally see is that, for example, a patient who falls sick while traveling cannot obtain his heart records in distant city for the benefit of because the healthcare providers at his hometown and the city are unfamiliar, so they cannot easily exchange any health information very quickly, right? And then the biggest thing is that because the data is not available in a standard format and it's also not centralized somewhere, because of that, a lot of healthcare organizations or research organizations which want to study population health scenarios or do any kind of population-wide studies that cannot do because there is no aggregated data and there is no standardization in this aggregated data somewhere. So that prevents us to do any kind of potential analysis of any medical errors, trying to study any kind of rehospitalization for chronic illness, what was the reason, why, and things like that, to come out with better efficient healthcare capabilities on those aspects. That would prevent us. There could be bottleneck to do any kind of research in healthcare, primarily because this data is not available for third-party folks to use in a way that would drive innovation and research in that space. The other most important thing is these healthcare systems are totally isolated, and they are very tied to a vendor and not easy friendly to integrate any kind of patient broadened devices, which today, as we see, many healthcare devices, patients can have an opportunity to do many healthcare devices, but the data generated by that is not primarily getting integrated into the patient healthcare system. So this is the whole goal has been to kind of drive towards a global standard, a single healthcare profile across for a patient across the US healthcare sector, so that his data is transparently, seamlessly available in real time to whichever provider he goes through, or to in a seamless way, in a quick and efficient manner. It's also accessible to the patient in real time, so that any updates are visible, and it's also deliverable in a way that it's understandable to the patient as well as the providers who are seeing the patient's data. So as I said, primarily the today vendor, there's no vendor. The systems are very specific to vendor. There's no vendor neutrality, and that's what drove towards an interoperability, which kind of benefits system integration, and the providers no longer need to be tied to a specific vendor. And also because of standardization, that'll help systems to interoperate and integrate and seamlessly exchange information across. So those being the limitations, what drove the FHIR standard. So to reiterate, FHIR is basically fast healthcare interoperability as an open community standard that was defined by the healthcare community, using which basically the premise has been to use the common industry standard web technologies to exchange healthcare information between different disparate systems in order to store and exchange administrative, clinical, and financial data primarily within the healthcare domain. So before when they started off FHIR, basically they set a goals as a manifesto, as a basis as to what these standards should evolve to and address. The primary focus has been on the implementation of the system. As the standardization happens, the system developers it should be easy for them to develop and deploy any systems. The standard should help the ecosystem of app developers to be easily understand the standard, to be build apps in a much more quick and efficient manner. So that's been the primary focus that they said. The again thought process was that the standard should make sure to address the common scenarios that is encountered in the healthcare domain, either the financial aspect of it, the administrative aspect of it, or the clinical aspect of it. The third important factor they choose was that it should be based on the latest modern web technologies, so that they can leverage. So you'll see that primarily they use the technologies, the web technologies like RESTful architecture, and which is based on JSON objects, which basically gives us greater readability in terms of understanding of the structure of the resources, or the messages that are exchanged between healthcare systems. Then the important thing is that the standard should be open, so that anybody should be able to use the standard to build on top of it any kind of applications or things, so it should be easily understandable in terms of for third-party app developers. Today, you see a lot of tech giants getting involved in healthcare sector because the standard is open. You see more innovation and investment coming into the sector. The other thing is they wanted to standardize in the kind of paradigms, architectural paradigms, in terms of how messages are going to be exchanged, what kind of protocols that we want to kind of use, what scenarios you want to use a particular mechanisms or methods of exchange. The fourth and the seventh important parameter was how do we demonstrate best governance of practices and how to ensure that the evolution of the standard is pretty much backward compatible. There is the governance on these standards in a structured way. For more details, you can refer to hl7.org/FIRE as to get a much more bigger background on the goals and the a bit more deeper overview on what FIRE is. So as we spoke about FIRE as a standard for interoperability, the basic four premises or paradigms of FIRE's interoperability is REST, which is an architectural style for information exchange in computing. Domain, how computers exchange information in an efficient way. Today, it's primarily used as a web technology. Then the messages for more bidirectional communication. REST is a more a client-server kind of a pattern, and the things like that. Then you have documents. Documents is basically the FIRE uses a compositional style of mechanism wherein it gives you an option to combine various resources and to create a document set around it. We'll be talking about much more details. And services, which basically is another paradigm which enables us to automate various financial and clerical workflows within the system, which kind of is very helpful feature of the FIRE's capability, FIRE's standard. So before we go into much more details in the FIRE, let's try to understand what REST is. REST, as I said, it's an architectural style based on HTTP, a web protocol, which is primarily used in the client-server architecture. You see a specific healthcare system talking to another healthcare system and requesting any information. We primarily use kind of a REST protocol to kind of get any kind of information from that system. That's how the systems exchange information. The basic unit of exchange of information, we call it as a resource, which in the REST paradigm, which basically is represented as an XML or a JSON schema. So basically defines that's a basic unit of element of exchange of information in a REST protocol. So every resource out is uniquely identified, what we call as REST URI, and that's how a client or a system that wants to request a particular resource would use the REST URI, the resource URI, to send a request to the server to say that I would like to read a particular resource identified by the resource URI, and the server would respond with the resource object corresponding to the URI. And so that fundamentally anything as a resource is addressable through the URI mechanism. And then fundamentally, as I said, the background of the REST architecture is primarily using the HTTP web protocol, primarily uses HTTP APIs. There are 4 fundamental APIs which are used doing CRUD operations. CRUD basically is create, read, update, and delete a resource, and on the HTTP paradigm for CRUD, we use post, read for get, update we use a put protocol, and D is delete in the HTTP world. So the REST basically fundamentally what it facilitates is a simple, stable interfaces, easy portable application and system deployment, high performance and scalability, and reliability is built on top of HTTP, because HTTP is built on TCP/IP, so that gives us reliability in the sense that when a client makes a transaction in the server, the transaction is guaranteed to complete. So you are never in a state where client and server are in different state. Either the transaction happens, it doesn't happen. Thereby, it ensures that the message exchange is always guaranteed to deliver to the server. So those are some of the paradigms what REST gives us. So as I said, resources, basically the FHIR interoperability standard, the basic unit of element of information exchange within the FHIR standard among computing systems is called a resource. This is the smallest discrete unit of exchange. FHIR gives you ability to group resources into documents or composable unit, because the whole paradigm of FHIR is that you can compose different kind of resources together and operate on it. There is a defined behavior and meaning about this resource. As I said, we talked about URI, which primarily fundamental way of identifying a resource within the healthcare ecosystem, and its resource is also the smallest unit of transaction of interest to healthcare. So now take a look at a typically small example about a resource representation. Here we are representing a resource patient as a resource. So on the resource structure, if you see, there are three aspects of the resource. Basically, the extensions where you can these extensions are additional things that you can add to the patient's record outside the context of the standard structure. Then you have a brief narrative of which is a human readable summary, which basically defines the name of the patient, the MRN number of the patient. Then you have a defined structure, which is more a standard, which basically uses codes and structured data elements to identify the patient resource. You have a unique identifier, a label, MRN, and the system of representation for MRN and the value that is associated with the patient resource. Then there is a family name, the given name, and a suffix, if any, and the gender, which basically refers to a particular system, which classifies the code value as an M for male. And then there is a date of birth and the provider organization, basically, which indicates the patient's association to a particular practice. So in that way, you can see there is a linkage between the service provider, basically the physician or physician's office is linked to the patient. So this would enable you to do any kind of queries. I can go to a provider and say, hey, give me a list of patients that are associated with me. You can then, this record should pull up. Similarly, if a patient wants to know who his or somebody else wants to know, the patient wants to know who the provider is, the patient can query this and he knows who the provider, and the provider's details are kind of interlinked. So there is demonstration of a relational model between the patient and the provider in this aspect as an example. In this slide, we see that how resources are being combined and visualized. On the left side, you see a diagnostic report. A diagnostic report, you would see a diagnosis being made. So there is an observation resource which indicates what the diagnosis basically shows, an imaging study that was done by probably a lab or which generates which observed the results. Then the organization, the practitioner to whom the report is going to be dispatched, and the imaging is about a particular patient. So there is references to each of the other resources in the diagnostic report resource. In that way, we would be able to see that there is a relationship established and a composition of various services, various resources to give a comprehensive picture on that. These resources are probably kind of, if you see that it's very distributed in nature, the observation resource could be hold within a different practice. The practitioner is a different provider, and then there's a patient in between. So, but they're all linked up as a cohesive unit and presented to different viewers of the patient's information in an efficient manner as applicable to them. So on the right side, you see that there is a patient subject. The observation, the diagnostic report is generated by a lab at hospital A, and then there is a practitioner who is also at hospital A who would like to view the diagnostic report, and the diagnostic report is about a patient. Even the patient can view the diagnostic report, and the organization that managing the patient is a different resource per se. So this is how the various resources within the healthcare domains shall be linked up to give her cohesive information about a patient. So far we talked about what FHIR is, what is a REST protocol, and then we talked about a brief overview on what resources means in the context of FHIR, and how now we look at how a FHIR resource is addressed. In this case, as we looked at patient as an example, as a patient resource, now if you want to kind of look at the patient record, you would see this is the endpoint. The FHIR server basically is the endpoint which is hosting this patient resource. So to query a specific patient with that ID, this is the URL that a computing system, for example, in this case, a provider wants to look up the patient information, whose patient ID is 1. The provider's system would send out a request to the FHIR server to pull this record, the resource information about this patient using this format of the URL. And for every resources that the healthcare ecosystem has is uniquely identified by an URL as such described here. So so coming back, as we spoke about, the kind of critical operations or fundamental operations that you can do on a resource are basically create, read, update, and delete, and the corresponding HTTP verbs or APIs for doing so are post, get, put, and delete. We will be exploring and how to use these APIs much more in depth, and with an example, we will see later how to use this on an actual FHIR server with a FHIR client interface for doing that. So far, we have discussed one of the message exchange the interoperability exchange paradigms, which is basically REST. So far in this tutorial, now we will be talking about one more paradigm, which is basically FHIR documents. Is another way of exchanging of information. FHIR documents is basically it's a compositional structure. Basically, it composes several different resources to give a more, and the resources that they're going to combine as part of the document is more cohesive in nature. Other fundamental difference when you look at documents is that it's an immutable set of resources, provides a fixed representation around these, and if you see that in this case, for example, you look at a discharge summary of a FHIR document, which basically has a certain set of resources that it has the clinical condition under which the person was admitted, who was the practitioner who looked after the patient, what's the name of the patient. So you have a patient resource that is linked to the discharge summary. There's a practitioner who linked to the discharge summary, and the condition under which, and what were the vital signs with respect to it. So there is a physical observation as well as the discharge medication. So all these combine to create what we call a discharge summary as a document. So in a typical use case where you want a FHIR document which is created, which is probably signed by the organization or the practitioner for that matter, is an immutable information that needs to be passed on, probably a primary care physician as a discharge report, so that the primary care physician is aware of what was his result. So documents helps us to kind of put that grouping of information and then be able to send out to the primary care physician system to share or exchange information on or the transitioning information from the hospital into the primary care ecosystem. So documents play a very important role in defining those kind of reports, exchange of those kind of reports in the clinical workflow. So, having seen two interoperability message exchange paradigms or data exchange paradigms in the FHIR standards, basically REST and documents, but REST doesn't, the FHIR standard doesn't necessarily indicate that the REST is the primary means of which you want to exchange any kind of data flow between different systems within the healthcare domain. FHIR messages is an alternative mechanism that can be leveraged to do any kind of inter-system communication. So FHIR message, the systems can operate purely by a REST mechanism or use purely a messaging mechanism or a combination of REST and messaging to keep support for both ends. The FHIR specification doesn't define what kind of messaging infrastructure to be used below, but it just define more at the data exchange or the data schema level rather than addressing the protocol level for intercommunication of these systems. So REST is an exception in that sense. So in this case, what we see is you have a combination of choices that you see that they can use messaging, you can use REST, or a combination of both. So, but when you take about messages as such, the structure of the message that is typically exchanged between the subsystems is on the right, which basically defines message as a bundle of resources, and you have a message header which basically defines what the message is. There's a message ID and things like that. Then you have some meta information about the message itself, and then you have references to various resources that are bundled together in that message that is exchanged between the subsystems. Now, the receiving end of the subsystem can, or the system that is a receiver of this message, can store the entire message as is, or it can organize the message in terms of resources. It really depends on the use case. So if you're doing any kind of analytics on the data, you would like to probably have these resources split upon and organize as independent resources rather than as a message. But if the focus is on purely on message exchange, the system might simply store the entire message as part of its data store. So have you seen in the case of message paradigm, we have seen the structure of the message here that is exchanged. There are typically two kinds of message exchange that is exchange patterns. One is synchronous and asynchronous, and the messages are of two types. One is request message and response message. A system sending a request to another system would receive back a set of response messages in reaction to a request message. And the pattern could be that a system sending a request is waiting for a response before it sends the next message. In the case of asynchronous wait, it doesn't wait for the response, it initiates a sequence of messages. So that's how a typical pattern is used in the communication, and the structure, the way it is bundled, is how it's depicted on the right. So this is another paradigm of addressing the interoperability requirement within the FHIR specification. So so far we have discussed three paradigms of interoperability: REST, documents, and messaging. The fourth paradigm is services. This is primarily closely associated with the integration of FHIR as a standard with the service-oriented architecture. It's primarily based on services. Services are very highly distributed, cohesive elements in the service-oriented architecture, which basically doing a specific business logic per se. In the case of FHIR, this would enable us to define workflows that are around specific individual resources or a collection of resources, which and the kind of exchange mechanism in the case of services is very lightweight messaging. The fundamental, however, in all these four paradigms is the exchange of resources primarily. In the case of the one typical example of the application of services is in the workflow of clinical decision support. One such example is if a provider wants to check if is there a problem with prescribing a medication X for a patient Y, he would invoke a service that would send out basic details, a lightweight message of patient details with the medication, and the service would probably do some assessment and give a feedback and saying that yes, yes or no, so that the practitioner can make a decision at the point of care. So that's typically what's the application of services in the case of fire context. So with that, we summarize the four interoperability messaging or message exchange mechanisms in the case of fire standards. So, but fundamentally, we need to remember that all these four paradigms still use, package, and exchange resources, which are a fundamental building block in the case of fire standard. This picture basically represents a healthcare repository model. It kind of demonstrates how resources which are hosted within the fire server are seamlessly shared across disparate health IT systems, and these systems have different unique interfaces with primarily you see tabs and other servers being used in the interaction, thereby giving that standardization makes the systems interoperate seamlessly and present the data in a view that is compatible to the kind of users that they're using that information, but the information itself persists in the fire server in a very standardized format, so that it's seamlessly exchangeable between different systems. To start off with, basically going back, the fire specification is broken down into a set of modules. If you see foundation, basically the basic definitional structure on which the rest of the specification is built, that's where the foundation is defines around. Then there is the implementation support, services to help implementers make use of the specification. There is security and privacy. Basically, it talks about documentation and services to create and maintain security and integrity and privacy. The confirmation is like how to test the confirmation to the specification and define implementation guidelines here. Then you have terminology is basically use and support of terminology and related artifacts when you want to integrate other systems like Snowbed and Lonit into things. Then you have linked data is basically defined methods of exchange of resources. That's what the exchange documentation of the standard specification around exchange talks about. Then you have administrative with basically around resources. It defines resources for patient tracking patients, practitioners, organizations, devices, and substances. Then there is record keeping and data exchange for healthcare process primarily, which is around clinical thing, which defines resources for problems, allergies, care processes, and things like that. Then there is medication management on defining how the medication management, immunization tracking, those kind of resources, and the documentation around that, where you for medications found there. And then they have diagnostic stuff, which is basically observation, diagnostic reports and requests, and related content goes into this standard. Then there's a workflow managing process of care, the clerical administrative automation of those kind of tasks. The documentation around the thing goes into the workflow management. Then you have financial, which is around billing and claiming support. That's the resources with respect to financial systems to interact with the health IT systems, other health systems. Those standards are defined in the financial section. And then there is the clinical reasoning, which is more about clinical decision support and quality measures. Those are standards in how you want to do real-time clinical decision making, so that it helps the practitioners, giving them real-time information to make more accurate prediction of patients' health. So these are the various building blocks of fire specification. If you would like to better understand more in details, visit hl7.org to get a much more detailed view on each of these subsections of the fire specification. So, as we address the interoperability mechanisms, what are the typical use cases of an HL7 fire standard? So one typical use case is, as we said, that the fundamental thing is on the personal health record, which is comprehensive information about a patient. Now, this health information needs to be accessed by other healthcare organizations which pay for healthcare to analyze the aggregated records to discern some trends. For example, you're doing a population-based study and you want to see a population health of a community as to is there any specific parameters that increases certain hospitalization in certain areas, or the whether the financial aspects make a different impact on healthcare in those kind of trends. So this information has to be standardized and be aggregated in a centralized way so that other systems can extract this information and do some kind of study or research or analysis around that. And you see a lot of, for example, in the case of because of standardization and availability of these information through REST and things like that, you see a new generation of APIs like Google and Amazon coming up, trying to tie up their cloud infrastructure of analytics and machine learning and accessing FHIR APIs and the data that comes out of the system, thereby building better health models and assessments as a feedback to and clinical decision support to practice or providers to make more accurate decision, which is much more safer from a patient standpoint of view. That's where the role of HL7 has been in the case of personal health. The other thing we already talked about, document as a mechanism for information exchange. We saw that discharge summary that was being shared from an hospital to a primary care physician. That's another typically an example. The other information that exchange, you want to kind of do any kind of radiology scans, imaging information, clinical letters, test result summary, those kind of things that needs to be exchanged between different providers within the system. The HL7 defines the concept of documents that will allow these kind of information to be explained. That is one typical way of applications of that are used across sharing of different providers. The third we saw about FHIR services, basically in the integration of FHIR ecosystem with the service-oriented architecture to kind of build them some kind of decision-making support. Clinical decision support is becoming a very significant factor in the practitioner's assessment of any medication prescriptions or at a real-time point of care kind of situations where the practitioner gets information in a real-time way so that he prescribes the right medicine rather than doing a trial and error on that. So that's another application of decision support. But there are several others kind of use cases that we typically see with around being around analytics and machine learning that is kind of fast penetrating. The other important aspects being that integration of IoT devices into the FHIR ecosystem. So, but for now, if you see from a FHIR standpoint, these are the fundamental building blocks or use cases that that FHIR was typically built around. So now, having said that, now what are the typical pros and cons of the FHIR interoperability model? What do we see as benefits, and what are the cons with respect to that? So, what are the positives? The basic thing is about positives is you have a great interoperability data model, an information model, which is kind of relationally designed for easy to consume for exchange of medical information across different IT systems. The second important thing is there is a wide FHIR community. Today you have a lot of innovation in terms of, because being an open standard, a lot of developer participation, technology company participation. The APIs and the tools are very easy to learn because they're purely adopted from the technology world. The FHIR is very easy to interoperate with legacy standards. FHIR also has a mechanism to easy to way to use clinical terminology because the FHIR specification already addresses how to integrate that. So these are some of the positive aspects of FHIR. But when it comes to the challenges, what we see is that being a generic information model is not always the easiest way to implement specific use cases. You already saw that in the case of extensibility, that the thing you probably you have to extend resources if there is some kind of a limitation in the way the FHIR model specification is not defined. So Then there always also you have challenges with respect to there is no backward compatibility. You see different standards like the DSTU3, D2, and other things. There is variation in the evolution of standard, but there is no backward compatibility around that. Then there is the fire extension profiles is an easy way to give you extensibility, but the challenges around understanding that and defining specifically in the health data or the health data around extensibility is quite a challenge, and it's a little bit complicated. Uh, Also, as there are many benefits of FHIR, but like standard, it comes with limitation. First thing is it doesn't define exactly, does not address the technology concern, such as system architecture, system integration, security, or analytics. Is purely a standard that was defined for interoperability. Uh, the standard set of APIs that have been designed might not be fully comprehensive for any kind of real-time applications, real use enough applications that we foresee in the future. And again, important thing is FHIR never specifies any kind of security protocol as such. So this is something that has to be done outside the FHIR specification, and also FHIR doesn't really address the infrastructure needs and so on and so forth. So these are typical characteristics which we see in other standards as a limitation that the FHIR has. So now we'll take a look at how to create a standard FHIR server for your own experiments. The FHIR server is basically based on a client-server architecture. You see a view on the left side of how a FHIR client will talk to a FHIR service, which is basically a server running on within a Jetty ecosystem. Then it's backed by a PostgreSQL database, which basically hosts the resources organized as a relational model for a FHIR service to expose that data for a FHIR client to consume. On the right side, we're going to show, we demonstrates the way the FHIR server, the SQL server are going to be deployed. We're primarily using a Docker engine within an Ubuntu ecosystem. The Ubuntu is basically a virtual machine running on top of a Windows OS. So that's the typical deployment view that we would be using for this building of this ecosystem. So there are several stages that to set up a FHIR server. Basically, first thing we need to do is build the FHIR server. We're going to use an open source FHIR server. We're going to modify the FHIR server to kind of integrate a PostgreSQL database. Then they're going to build it. Then we're going to deploy the FHIR server using the Docker engine. See that the FHIR server is up and running. The next step is the FHIR server itself doesn't really contain any data. What we're going to do is generate a sample data set, which we're going to feed in into the FHIR server through uploading the sample data set. Then we are going to verify that we are able to query the data set which is uploaded. That kind of sum ups the way how to set up a FHIR server. So the basic first step is to kind of build a FHIR server. Is we're going to clone the FHIR server, then we're going to set up the happy.properties file where there are key value pairs for configuring the database interfaces. So we're going to configure the setup or change the configuration as mentioned in this slide. Then we're going to update the POM file to download the Maven dependency for a PostgreSQL database. Then we're going to do a Maven clean install. For this experiment, we're going to skip any integration test we run, so just to optimize the process. Once the server is built, the next step is to do a Docker compose, basically to compose the image of database and the FHIR server together. We would edit the Docker compose file, copy the contents as mentioned here into the Docker compiler and save it. This basically helps us to build the Docker compose. Once you're executing the Docker compose image, as the command mentioned in the previous slide, you would see that the Docker compose will build and deploy the server and the database. Once that happens, you can go visit, pull up the web page using the following URL. This would display the following page. Once the page is done, the next step is to kind of do to the data generator. Basically, you git clone this, follow the steps. It would generate a sample data set, which is going to be an STU3 based data standard. Once the data set is generated, the sample data, the next step is to upload. For the uploading, we're going to use the data uploader tool, basically the tag uploader. We would follow the instructions as mentioned here. we would git clone, modify the package JSON to kind of include the repository. Then we'll build out the things and execute the last two commands to upload the information. The URL is the URL of the Fire server that we have already started. So that would go and upload the data into the Fire server. This would take a while because the amount of data that it's going to upload is going to be pretty huge. Once that is done, to verify that, we go back to the URL, select patient resource and resources structure. Then we're going to look at the search window that would appear. We are going to pull up records by active patients. Once we select and search active patients, the Fire server would return all the patient records which are currently active, and you should be able to browse through each of the patient records. So that would end how you would go through the series of steps to set up a Fire server, upload data, configure data, and then make sure that the data is populated. Please follow the YouTube link for much more detailed instructions on how to set up the Fire server. In this section, we're primarily going to be talking about CRUD operations on Fire server. CRUD basically stands for create, read, update, delete, which is the primary fundamental operation that we can do on a Fire server using RESTful APIs. Primarily, in the last section, we did go through how to set up a Fire server. Then we kind of generated a sample data set, inserted the data set into the Fire server, and did some sample queries on the Fire server using through the browser on a Fire server URL, where we will look up the patient record. This is more like now that Fire setup has been set up. Now we'll create a Fire client, basically, which can do these operations on the Fire server. This slide basically depicts how the Java Fire client will be used with the Java Fire server. Basically, at the top of the model, you see the diagram that where an Happy Fire client will do an HTTP interaction with the Happy Fire server. We will use some of the Java generated Happy model object, which kind of gives us the APIs to be used with the RESTful client to kind of populate the information, which would then get generated, translated into a JSON message, which would be posted over an HTTP to the Fire server, and then posted into the PostgreSQL database. The basic APIs that would need for us to kind of create a RESTful client interaction is we need to kind of establish the standard that we want to use, and in this case, we are going to use the DSTU tree. So that will establish and set the context, and from using the context API, the return of the content of the context API, you want to create a RESTful client with the path of the server, the Fire server as an input. We are going to use a generate client interface based on that. Below are the list of DSTU3 resources that we would be using in these examples to kind of demonstrate basic CRUD capabilities. For more information, I would request you to look at the reference material on the Java Fire client capabilities in the GitHub link that was mentioned. There is also a bunch of examples that can be used as a reference material for creating a Fire client and exercising some of the RESTful API interactions, which are more comprehensive than the one that we want to demonstrate today. So, as I mentioned, that we would be talking about 4 important CRUD capabilities using the RESTful APIs, the HTTP APIs that we would be using. One is create. The create is basically to demonstrate any creation of a new resource on the server. We primarily, for a create, post is the HTTP protocol or the API name that we will be using. Read, anything to do with the read of a resource, get API, HTTP GET protocol or an API is used. For updates, we generally use put as an update, which you want to update an existing resource, and delete operation to delete a resource identified by the resource ID. So most of these transactions have a link to the resource ID that the create operations create a resource and return you the ID, which can be used as an input to refer to that ID for subsequent operations. So now in this slide, we're basically looking at how do you create a patient resource using an HTTP post kind of thing. API, the post API is pretty much hidden inside the client library. So here we see a generic client being created with the server URL. Then we look at resource, basically the patient resources being created once with the instantiation of the patient object, then the patient specific information, the family name, given name, and the suffix, the gender, and an identifier, which is basically a unique identifier that has been added and set, and saying that the patient the status is set to active. And then there is a request that is being posted using client.create, which would send out a post request onto the server, and on the response we extract the resource ID that was created for that patient and return to the user to be used for subsequent operations. So the next operation is about how do we update a particular patient resource given the resource ID of the record within the database, and then you want to kind of update a phone number. So the contact point gives us the basic structure to kind of fill in the information with respect to the to phone number, email, and etc. Here we demo the home phone number being updated, and there's corresponding to resource patient whose resource ID is given as part of an input parameter, and then a request is sent which would go and update the specific user record. The next API what we're primarily looking at is, as part of the CRUD thing, is more about read operations, which is basically using HTTP GET. Here we try to showcase how a patient record, the patient name of the patient that associated with a particular patient record is returned, a resource ID is being passed as an input, and then a GET request is sent to the server, and the patient name is returned to the user. That's how you basically do a GET request. And deleting a particular resource. In this case, we would like to demonstrate that we want to delete a patient record. We pass in the patient record ID or the resource ID that is associated with it, and then we do a delete operation on the client and return the response as the ID of the resource that was deleted from the server. For a client usage demo example on how to do CRUD operations, please refer to the YouTube link for more details. So bundles is a unique concept, which is basically a resource bundle. It's a way, a container to hold a collection of resources. The primary example in this case is where typically you see that bundle implementation is in the case of a search result or a history information or a bunch of messages that are grouped together and they want to kind of be operated upon, is where bundles are used to represent it as a container. So for example, in this use case, you see a typical Java application of how the bundle is typically used. In this example, what it demonstrates is a system is doing a RESTful query to a file server wherein it wants to retrieve a patient record whose name is John. And this query could return many records because there could be many patients with the name John. And so in this case, as you see, there is a bundle response which it assumes when a person with that particular name is searched for, there could be records which are more than one that is written, or more than 10 or 20 records that is written. And you see that where the API makes a call and then returns a bundle. And if you see that the bundle entry could return a set of records as well as a link to next set of records. And this is typical implementation of where you want to traverse through a chain of records which have been mapped, which have matched the criteria, and typically you see in a typical server implementation, it could return you 20 records at a time, and then once you have processed those 20 records, you want to kind of redo a query for the next set of 20 records. And the bundle has mechanisms that are built in, because bundle is a container of resources that are retrieved. And through the bundle APIs, you can do subsequent queries. It is basically the concept of paging, where you have a bunch of pages that is returned, then you have a link to the next bunch of pages that you want to retrieve, and bundle is typically a container of pages per se, and that's when the bundle capabilities are typically used, and that the standard define bundles as a mechanism to handle a group of resources. So far, we have discussed about various aspects of fire standard as a specification, fire protocols, interoperability mechanism, how does it address, and some of the mechanisms, way the resources are managed and handled and exchanged and queried for in the fire standard, what are the mechanisms the fire standard defines around. Now we would go to specifically look at what are the typical fire data types that are defined, how do we extend those capabilities, how do we extend the fire resources capabilities itself, what are the typical operations additional operations that are defined on the fire, apart from the basic CRUD operations that we have typically seen in the earlier slides. So we have we'll talk about fire data types. Fire data types basically the fundamental building blocks around which resources are defined. This is the next level of granularity that you have to identify individual elements, which the general purpose data types themselves derived from the primitive types. Typically the kind of things that is based on the domain concepts. For example, you have annotations, the period, the range, the human name, the contact point, the address, the signature, and so on and so forth, which are typically more a domain concept that you generally see. So the fire defines a wide set of data types, both primitive, general purpose data types, and also special purpose data types, which are typically used to compose resources into resources per se for in information, so that you can uniformly represent the data on different end systems. So fire extensions is a unique capability that is given within the fire standard. There could be scenarios where that you would like to extend a resources definition beyond what is the standard definition. That's when the extensions are used. So one primary example is sometimes you have a policy of a patient with respect to consent, sharing his health record, and probably a patient health recording service which is hosting the patient record can expose this policy through an API. Now, some other subscriber of this information can use this policy and add extensions to the policy through this extension mechanism, so thereby giving an extension or added capability to the patient's consent information. So that's how the fire extensions are typically used. Fire operations provides a different paradigm, not necessarily from a REST point of view, which doesn't fully suffice for certain use cases. See, the rest the fire operations is more in the design and the concept of RPC mechanism, where when a request is made, a server needs to do more than what it just returning a records. In that case, it has to formulate or design the response appropriate to a request. So in those kind of scenarios, you would probably typically use a fire operation. This could typically involve that the server execute a sequence of business rules. Typically, this in a clerical scenario, when a request is made, you want to kind of do n different things based on the context of the request, and then return a response on that. Doing that kind of workflows, fire operations is typically very useful for doing that. To summarize and kind of review back to about what we learned, FIRE is basically a fast healthcare interoperability resources, a standard driven by community, basically using web technologies like JSON and XML through the use of RESTful APIs based on HTTP protocol to store, exchange clinical, financial, and administrative information in the healthcare sector. It basically provides XML JSON-based syntaxes, various methodologies, resources as fundamental building blocks on which the APIs can be exercised, an ability to compose these blocks into documents, and then the bundles wherein you want to kind of do several kind of capabilities like search the history of the patients and things like that, which gives you the ability to do queries and so on and so forth. Apart from that, it is very easy to read. We have seen that because of the XML and JSON standard, it's pretty understandable. It's more human readable. We see multiple paradigms of communication capability that it provides in terms of REST and messaging. We've also seen how the documents as a resource is used to combine different kinds of resources to kind of give a holistic picture of things, and the services wherein you can build on business services and capabilities that are more critical for administrative and financial needs, or other kind of stuff that we can do with the services capability. Finally, coming to a review of FHIR Manifesto. Why was it created? The basic fundamental being that intent was focused on implementers so that we can build excellent apps, easy to build apps kind of thing. Variety of common scenarios, leverage industry technologies so that you're interoperable standard, so that you're not tied to a vendor, and you should be able to interoperate with any diverse distributed systems, healthcare systems family. The readability to a human being is easy, right? So make the content easily available for anybody to consume, support multiple paradigms and architectures, and also demonstrate best practice governance. So you can refer to more on FHIR at hl7.org, which gives you much more details on what FHIR and FHIR capabilities and its evolving nature of the standard. So for references for this presentation, I did refer to the HL7 FHIR specifications and several use cases that we see on the applications of FHIR per se. Then the other material that have been presented previously by different industry veterans who have showcased the capabilities of FHIR and used in different contexts. With that, I conclude my FHIR presentation. Thank you for listening.